All right, this is April 15th and variation word problems. So just like we learned yesterday, we're going to be dealing with only direct and inverse today. And we use direct in situations where as one variable increases, the other variable also increases. So this could be like hours worked and your paycheck. That is our typical example for that. The more hours you work, the bigger your paycheck's going to be. The smaller hour or the less hours you work, the smaller your paycheck's going to be. And then we also have inverse, where as one variable increases, the other decreases. So this typical example that we use is a road trip, where our two variables are time and speed, right? So if your speed increases, your time is going to decrease. The faster you go, the slower it takes to get there. It also works the other way. The slower you go, if your speed decreases, the time is going to increase. So dealing with just direct variation examples where they both will be increasing, the sales at a baseball game vary directly with the number of people attending. So we're going to box in this varies directly and look for the two things on either side of it. So the sales and the number of people is what we're discussing here. We'll set up sales as S equals K for our constant variation times P. So the sales for this game were $12,000 when 800 people attended. So to solve for K, we'll divide by that 800. And then K will be, if we do 120 divided by 8, that'll be 15. So that K here is the cost of the ticket, just $15 per ticket. So every single time I want you to set up that 15 and plug it back in. Then we're going to plug in either sales or people, whichever they give us. So if it's 12,000 when 800 people attend, determine how many people attended if the sales are 15,000. So obviously the sales increased from 12,000 to 15,000. So our number of people are going to have to increase as well. They didn't make more money with less people showing up, right? So as one goes up, the other goes up. So in other words, our final answer should be something greater than 800. So we're going to divide by 15 to solve for not K, we're solving for P here, the number of people. And then that will be 1,000. So that'll be 1,000 people that showed up, which makes sense. Increased from 800, just like the 12,000 increased to 15,000. And this is really important stuff, and stuff that you will see applicable to the real world. So ounces of medication varying directly with the weight of the patient. This is really important, especially for anesthesia and anytime you are having to have a surgery where an anesthesiologist comes in and puts a person under. They need to know exactly how much and of what type of medicine and how much you weigh and different things like that. So ounces of medication, we'll just call that O, varies directly with the weight of the patient. So better yet, let's change that to medication. O could be confused with a 0. So medication varies directly with the weight. So a 120-pound adult, the weight requires 3/4 of an ounce of medication. So I'm going to leave that as 0.75. We would divide by 120, and that will leave me with 0.00625, if I'm not mistaken. 2 zeros, yep, good. So then we take that and we plug it back in to our original equation. And now it says how many ounces of medication are required for a 200-pound adult. So we're going to plug in 200 for the weight, and that will be 1.25. So I remember this problem because I always talk and discuss this same thing from previous semesters about how this is really important, right? So you don't want to give the 200-pound adult the medication that you would need for a 120-pound adult. That 200-pound person is going to be feeling what's happening in surgery. Not good, right? And then the same thing, you don't want to give a 120-pound adult the medication that somebody would need for 200 pounds, because that person either might stay under way too long or something worse could happen, right? So this is really, really important stuff that is applicable to what we're talking about with variation. All right, I'll let you do 3 and 4. It's pretty much the same thing, but going down to 5, this one's where it gets a little different. They're just asking for the constant of variation here, so we're just solving for k. So the income of a computer analyst varies directly as the number of hours worked. So the income varies directly as the hours. So I'm going to say paycheck, and that varies directly as the number of hours worked. So if the analyst earned $256 for working 8 hours, he's got a really good job. Divide both sides by 8. 256 divided by 8. That'll be 32. That is really, really good. So that's our constant of variation. And in this case, that 32 is $32 per hour. That's how much he's making per hour. Very, very nice. And then for number 6, the gallons of water used to take a shower varies directly with the number of minutes. So we're going to say gallons vary directly with the minutes. So if an 8-minute shower uses 48 gallons of water, we will plug in 48 and 8, solve out for k, and that k, not m, will equal 6. So that constant variation is 6, and that represents how many gallons per minute, right? So I don't know if this is completely accurate. I'm sure it kind of varies, but think about that the next time you take a shower. The gallons of water, that would be 6 gallons of water per minute. So those of you guys that have taken like 20-minute showers and 10, 15-minute showers, like that's a long time. Inverse variation. So this will be as one variable increases, the other decreases. And we have our typical inverse variation example here with time, and it varies inversely with speed. So time traveling varies inversely. So the time when traveling, I saw time traveling, and I'm like, what in the world? Time traveling? I thought this was relevant examples. No. So time varies inversely with the average speed. Just don't even worry about that, okay? Some Marty McFly stuff right there. Hope you get that reference. If not, go watch Back to the Future in your free time. It's a great one. So if a train travels between 2 cities in 3 hours, we have time and how it varies inversely with speed. So we put that variable on the bottom. And then 3 hours is our time and an average speed of 65 miles an hour. So that will be 195 as our K. We set this back up with 195. Don't plug in a variable yet. Now, how long time would it take at an average speed of 78 miles per hour? And that would be 2.5. So you see that as our speed increased from 65 to 78, our time decreased from 3 hours to 2.5 hours. So that makes sense. For number 8, a company that produces laptops has determined that the number of laptops it can sell varies inversely to the price. In other words, if you have a MacBook Pro or whatever the really nice MacBook is, and it's selling for, $2,000, $3,000, I don't even know how much it is, not many people are going to buy it. But if there's a MacBook Pro out there for $200, everybody would buy it, right? So depending on the price, that's how many people are going to buy it. As that price goes up, less people will buy. As the price goes down, more people will buy. So the number of laptops, we'll call it L, varies inversely with the price. So 2,000 laptops are sold when the price is $2,500. So for our K there, that will be 5 million. And then we will plug that in back into our original equation without plugging in anything. And now we'll look at that final question. How many laptops can be sold if the price of the laptop is $1,000? So they dropped this laptop like by $1,500. That's a crazy amount. We should get a much higher number of people buying it now. So we are dividing that by the price, which is now 1,000. And you see these ending zeros right here. As long as they are both ending, you can mark those off. If there's a 1 right here, if this was like, 10,001, that obviously wouldn't work. But that just leaves us with 5,000 over 1. So our answer is 5,000 laptops. So the price went down, but instead of 2,000, it went to 5,000. Our number of laptops increased. For number 10, the number of workers varies inversely with the time and days it takes to complete the project. So we'll talk about workers and how that varies inversely with the number of days. So 5 workers can complete a certain project in 24 days. So that will be 120. And we will plug that back in. And then it says how many workers will be needed to complete the project in 15 days. So in other words, we're asking how many workers if we do it in 15 days. In 120, I believe that will be 8. Yeah, 8. And make sure you put 8. I did exactly what I was about to tell you not to do. So make sure you put the correct answer here in the correct unit, because sometimes people will put days and the question asked for workers, right? So if I ask you, hey, how many people do we need for this job? And you say 8 days, I'm going to look at you like you're crazy. Like, what the heck? I said how many people, not how much time, right? So the workers are 8 workers. Make sure that you do that correctly and write that down correctly. Lastly, I'll do number 12 with you. The cost per person to rent a cottage in the Outer Banks is inversely proportional, or varies inversely, that means the exact same thing, to the number of people who share the rent. So in other words, the cost varies inversely with the people. Cost varies inversely with the people. So we're just asking for constant of variation here. If 7 people share it and it costs $42 per person, so we can multiply that out, and K would equal 294. So what that K is right here is how much it costs in total to rent out that cottage. Now, if you had increased the amount of people, say you have some air mattresses and somebody sleeps on the couch, then that cost per person will decrease. Say you had 10 people instead of 7, then that cost will be a little under $30 instead of $42 per person. So that's really, really good. And that's a